Did war invent technology or accelerate it? Throughout history, humanity has fought countless wars. And every war has driven the development of new weapons and new technologies. Among them, however, one conflict stands above the rest. Many historians consider the Second World War to have had the greatest impact on technological progress. People often say that World War II created radar, gave birth to computers, and invented nuclear power and the jet engine. Books and documentaries frequently present these technologies as if they suddenly appeared because of the war. There is no doubt that World War II was the largest and most resource-intensive conflict in human history. Nations poured enormous amounts of money, manpower, and scientific expertise into military research and industrial production. As a result, we often hear a familiar claim: war created modern technology. Today, we'll explore some of the technologies that shaped our modern world and discover whether World War II truly invented them, or simply pushed them forward faster than ever before. The question becomes even clearer when we look at nuclear technology. Research into nuclear energy had already begun long before the Second World War. Scientists had discovered radioactivity, studied the structure of the atomic nucleus, and the properties of neutrons, and by 1938, had already discovered nuclear fission in uranium. However, this research was still largely at the stage of basic science. Scientists understood that nuclear fission could release enormous amounts of energy, but they had not yet developed nuclear reactors capable of sustaining a controlled chain reaction, nor did they have the industrial facilities needed to produce fissile materials on a large scale. Then the Second World War began. Fearing that Germany might develop nuclear weapons first, the United States launched the Manhattan Project. The project involved approximately 130,000 people and cost about $2 billion at the time, equivalent to tens of billions of dollars today. With such an extraordinary concentration of manpower, funding, and scientific expertise, nuclear technology advanced at a pace never seen before. Scientists and engineers built massive facilities to separate and enrich uranium, established methods for producing plutonium in nuclear reactors, and rapidly improved technologies for controlling chain reactions, measuring radiation, and handling radioactive materials safely. After the war, these technologies, facilities, and highly trained specialists began to serve a very different purpose. Engineers developed nuclear power by controlling the heat produced during nuclear fission, using it to generate steam that drives turbines to produce electricity. In 1951, the Experimental Breeder Reactor 1, or EBR-1, became the first reactor to generate electricity from nuclear energy. In the years that followed, nuclear power plants were built around the world. Of course, an atomic bomb did not simply become a nuclear power plant. A nuclear weapon is designed to release an uncontrolled chain reaction in an instant. A nuclear power plant, by contrast, must maintain the same nuclear fission process safely and continuously over long periods of time. The two technologies were built for entirely different purposes. Even so, there is little doubt that the reactor technology, nuclear fuel production capabilities, radiation measurement techniques, and skilled workforce developed through the Manhattan Project became an essential foundation for the growth of civilian nuclear power after the war. Ultimately, this example shows that the war did not create an entirely new science from nothing. Instead, it concentrated enormous resources on research that was already underway, dramatically accelerating the practical development and industrialization of nuclear technology. The next technology we'll explore is radar. Radar is a technology that transmits radio waves and analyzes the signals reflected back from objects to determine their location and distance. Many people believe that radar was invented in Britain during the Second World War. But that isn't actually the case. Scientists had already discovered by the late 19th century that radio waves could be reflected by objects, and researchers in several countries were actively exploring ways to use radio waves to detect ships and aircraft. Britain had been developing practical radar systems throughout the 1930s, before the war even began. In fact, by the time the Second World War broke out, Britain had already deployed an early warning radar network known as chain home, along its coastline. In other words, radar was not a wartime invention that appeared out of nowhere. What the war did was push radar technology to an entirely new level. Military forces needed to detect enemy aircraft from much greater distances, track them accurately at night and in bad weather, and reduce the size of radar equipment so that it could be installed not only at large ground stations, but also on ships and aircraft. These demands drove rapid advances in radar technology. A major breakthrough came in 1940 with the development of the cavity magnetron in Britain. This device could generate far more powerful microwave signals than previous systems, making it possible to build radar that was both more capable and much smaller. After the war, radar technology quickly spread into civilian applications. It became an essential part of air traffic control, helping aircraft operate safely. Weather radar made it possible to monitor the movement of typhoons, thunderstorms, and heavy rainfall in real time. Radar also became indispensable for marine navigation. Today, it is even used in automobiles to measure the distance to vehicles ahead and detect nearby obstacles. But radar's impact did not end there. The magnetron developed for wartime radar unexpectedly led to another important invention. In 1945, American engineer Percy Spencer noticed that a chocolate bar in his pocket had melted while he was testing a radar magnetron. After confirming that microwaves were responsible, he carried out a series of experiments and eventually developed a device that could heat food using microwave energy. That invention became the world's first microwave oven. In the end, radar was not a technology created by the war. Instead, it was an existing technology that advanced dramatically under the pressures of war. And the microwave technology developed along the way eventually found its place, not only in airports and weather stations, but also in the kitchens of millions of homes around the world. The next technology we'll explore is the computer. Today, computers have become an essential part of our daily lives. However, the idea of a computer existed long before the Second World War. In the 19th century, the British mathematician, Charles Babbage, designed machines that could perform calculations automatically. By the 1930s, researchers in several countries were already developing electromechanical, calculating machines. Around the same time, the British mathematician, Alan Turing, established the theoretical foundation of modern computing by describing a mathematical model of a general-purpose computing machine. When the war began, however, the demand for large-scale calculations increased dramatically. Calculating artillery trajectories, processing radar data, and, above all, breaking German military codes required far more computing power than humans could provide by hand. To solve this problem, Britain developed Colossus, an electronic computing machine designed to help decipher encrypted German messages. Meanwhile, in the United States, ENIAC was developed to calculate artillery firing tables for the U.S. Army. Funded by the U.S. Army, ENIAC became the world's first general-purpose electronic digital computer. Although it was completed only after the war had ended, and saw little military use during World War II, it demonstrated that large-scale electronic computing was practical and marked the beginning of the modern computer era. Of course, these early computers looked very different from the machines we use today. They filled entire rooms, contained tens of thousands of vacuum tubes, and consumed enormous amounts of electricity. Even so, they performed calculations at speeds that far surpassed human capability, and proved that electronic computers could become a practical reality. After the war, computer technology continued to advance. Technologies originally developed for military purposes spread to universities, research laboratories, and private industry. Vacuum tubes were eventually replaced by transistors and integrated circuits, making computers smaller, faster, more reliable, and far less expensive. In the end, computers were not a technology invented by the war. Rather, the war accelerated the practical development of ideas and research that already existed by concentrating unprecedented levels of funding, talent, and scientific effort. The next technology we'll explore is penicillin. Many people believe that penicillin was invented during the Second World War. But that isn't actually the case. Penicillin was discovered in 1928, long before the war began, by the British bacteriologist Alexander Fleming. He noticed that bacteria failed to grow in the area surrounding a certain type of mold. However, making this discovery was only the beginning. At the time, extracting penicillin in a pure form was extremely difficult, and even producing small amounts was a major challenge. More importantly, there was no practical way to manufacture enough penicillin to treat large numbers of patients. Then the Second World War began. On the battlefield, infections caused by gunshot wounds and blast injuries became one of the leading causes of death among wounded soldiers. In many cases, soldiers survived their initial wounds, but later died from bacterial infections. To solve this problem, the Allied nations invested enormous resources in the development of penicillin production. Governments, universities, and pharmaceutical companies in both Britain and the United States worked together to turn penicillin into a practical medicine. As a result, penicillin, which had once been produced only in laboratories, could now be manufactured on an industrial scale. By the time of the Normandy landings in 1944, production had increased enough to supply penicillin to large numbers of wounded Allied soldiers. After the war, these manufacturing techniques continued to improve. Penicillin quickly spread beyond the military into civilian hospitals, where it became widely used to treat bacterial infections, and marked the beginning of the antibiotic era. In the end, penicillin was not a medicine invented by the war. Rather, the war transformed penicillin from a laboratory discovery into the world's first mass-produced antibiotic, making it available to millions of people and forever changing modern medicine. The next advancement we'll explore is blood transfusion and blood management. War claimed countless lives. Yet ironically, it also drove major advances in medical technologies that saved lives. One of the best examples is the development of modern blood management. What the Second World War advanced was not simply the technique of blood transfusion. It was the entire system for collecting, testing, storing, transporting, and rapidly delivering blood to patients who needed it. In fact, blood transfusions had already been performed long before the war. However, blood could not be stored for very long, and transporting it over long distances was extremely difficult. More importantly, there was no reliable system capable of supplying blood to thousands or even tens of thousands of patients. Then the Second World War began. Every day, the battlefield produced large numbers of wounded soldiers, and severe blood loss became one of the leading causes of death. To address this problem, the United States and Britain invested enormous resources in developing a large-scale blood supply system. National blood donation campaigns were organized, while techniques for refrigerated blood storage and long-distance transportation were rapidly improved. At the same time, methods for separating and preserving blood plasma advanced significantly. Unlike whole blood, plasma could be stored for much longer periods. It could even be dried into plasma powder, making it far easier to transport to frontline hospitals. As a result, field hospitals were able to perform blood transfusions much more quickly, saving the lives of countless wounded soldiers. What made this achievement so important was that it was far more than a single medical breakthrough. It was a national-scale medical system. Governments, research laboratories, hospitals, blood donation organizations, transportation networks, and refrigerated storage facilities were integrated into a single coordinated system. For the first time, a reliable large-scale blood supply network became possible. After the war, this system became the foundation of modern blood banks. The blood donation programs, blood storage techniques, and emergency transfusion systems we rely on today all grew from the technologies and experience developed during that period. In the end, the Second World War did not invent blood transfusion. Instead, it transformed the way blood was collected, stored, transported, and delivered, laying the foundation for the modern blood management system. The next technologies are synthetic rubber and nylon. Neither of these materials was invented during the Second World War. Both had already been developed years before the war began. The problem was production. They were expensive to manufacture, and only small quantities could be produced. As a result, Their use was limited to a few specialized industries. Everything changed after the outbreak of the Second World War. In 1942, Japan captured many of Southeast Asia's natural rubber-producing regions, creating a severe rubber shortage for the Allied nations. Natural rubber was an essential material for almost every piece of military equipment. It was used in automobile and military truck tires, tank components, aircraft, electrical wiring, gas masks, and countless other military products. Without enough rubber, it became impossible not only to manufacture new equipment, but also to keep existing vehicles and weapons operating. Recognizing this as a national emergency, the U.S. government invested enormous resources into solving the problem. It brought together universities, chemical companies, and rubber manufacturers into a coordinated research and production program, while simultaneously building new factories dedicated to synthetic rubber. As a result, polymerization processes and quality control techniques improved rapidly, and production expanded dramatically within just a few years. After the war, these manufacturing technologies spread into the civilian economy, providing the foundation for modern automobile tires and countless rubber products that we use today. Nylon followed a remarkably similar path. It had already been invented in the 1930s and was originally marketed as a consumer product, most famously in women's stockings. But once the war began, its role changed completely. At the time, most silk used for parachutes came from Asia. When wartime supply routes were cut off, the United States urgently needed a replacement. Nylon became that replacement. The U.S. government redirected nylon production toward military use and rapidly expanded manufacturing capacity. Researchers also worked to improve its strength and durability, so it could be used for parachutes, ropes, military tents, equipment straps, and many other military applications. As a result, nylon became one of the most important materials used in wartime equipment, while production technology advanced at an extraordinary pace. After the war, these advances quickly spread into civilian industries. Nylon found its way into clothing, sports equipment, industrial fabrics, automotive components, and countless everyday products, eventually becoming one of the world's most important synthetic fibers. In the end, the Second World War did not invent synthetic rubber or nylon. It made their large-scale production possible, laying the foundation for their widespread use in modern industry. The next technology we'll examine is the jet engine. The basic concept of the jet engine had already been developed before the Second World War. In 1930, British Royal Air Force officer Frank Whittle patented a turbojet engine. A prototype powered by his engine successfully flew in 1941. Around the same time, German engineer Hans von Ohain was independently developing his own jet engine. In 1939, Germany's Heinkel HE-178, powered by von Ohain's engine, became the world's first aircraft to fly using only a jet engine. So the jet engine was not a technology suddenly invented during the war. However, the Second World War dramatically accelerated its development. At the time, propeller-driven aircraft faced aerodynamic limits as they entered higher speed flight. Building fighters that could fly faster and higher required an entirely new form of propulsion, beyond the traditional piston engine and propeller. Germany and Britain poured enormous resources into the race to develop jet engines. A jet engine generates thrust by compressing air, burning fuel, and ejecting hot exhaust gases at high speed. But turning this principle into a practical aircraft engine required solving many engineering challenges. Engineers needed turbine materials that could withstand extreme temperatures and high rotational speeds. They also had to improve compressor designs capable of compressing large volumes of air efficiently, while developing fuel and combustion systems that could operate reliably without flame-out. As wartime research and investment intensified, these technologies advanced rapidly. As a result, the jet engine evolved from an experimental concept into a practical power plant for military aircraft. In 1944, Germany introduced the Messerschmitt Me-262, the world's first operational jet fighter. The Me-262 was significantly faster than most propeller-driven fighters of its time, and clearly demonstrated that jet aircraft represented the future of air combat. However, it also suffered from short engine life, limited reliability, fuel shortages, production delays, and a lack of experienced pilots. Because it entered service too late, it was unable to change the course of the war. Even so, the Me-262 proved that jet engines were no longer just experimental technology. They were ready for real-world aviation. After the war, the technology advanced even more rapidly. More powerful and reliable engines, combined with new aircraft designs, enabled fighters to break the sound barrier and reach speeds and altitudes that had been impossible for propeller-driven aircraft. The technology soon spread into civil aviation. As jet engines became more powerful and efficient, long-range jet airliners emerged, and the jet engine became the foundation of modern air transportation. In the end, the Second World War did not invent the jet engine. Instead, it brought together national research efforts and accelerated the transformation of the jet engine from an experimental concept into one of the defining technologies of modern aviation. The final area we'll examine is food engineering and military rations. Many people know that soldiers during the Second World War ate large amounts of Spam. But what the war truly advanced was not a particular food. It was the science of preserving food, transporting it safely, and providing the nutrition needed to support millions of soldiers. In fact, canning technology had existed since the early 19th century, and research into food preservation had been underway for many years. However, production was expensive, and no system yet existed that could supply food efficiently to massive armies over long periods of time. Everything changed with the outbreak of the Second World War. Providing a reliable daily food supply for millions of soldiers became just as important as fighting the war itself. Military rations had to last for long periods, survive long-distance transportation, remain lightweight, and still provide enough calories and nutrition. To meet these demands, the United States invested enormous resources in developing military rations. The government brought together food companies, universities, nutrition scientists, and military research organizations into a coordinated development program. As a result, standardized combat rations such as the C ration and K ration were developed. Canning technology continued to improve, while new methods for dehydrating and concentrating food greatly reduced its size and weight. Nutritional science also advanced rapidly, allowing calories, protein, vitamins, and other nutrients to be carefully calculated and balanced for military use. Spam also played an important role. Although it had been introduced before the war, its long shelf life, easy transportation, and suitability for mass production made it one of the Allied forces' most widely used military foods. After the war, these advances did not remain within the military. Large-scale food manufacturing, quality control, preservation, and packaging technologies spread into the civilian food industry. They laid the foundation for many of the canned foods, instant meals, frozen foods, and dried foods that are common today. In the end, the Second World War did not invent new foods. Instead, it transformed food engineering and military logistics by advancing the large-scale production, preservation, transportation, and scientific nutritional management of food. Looking back, all of these examples shared one thing in common. The Second World War did not invent most of these technologies. Instead, it brought together science, industry, and national resources, allowing existing technologies to develop far more quickly than ever before. Ideas that had remained in laboratories became practical technologies, and their impact continued to shape the modern world long after the war had ended. Thank you for watching, and see you in the next video.